Hello everybody, I welcome you all to the subject Electromagnetic Field Theory. Here we are in chapter number 7, that is Steady Magnetic Field, and this is the 12th video. Up till now in the steady magnetic fields we have seen the major topics, that is current distributions. We know that the electric current, that is DC current, causes magnetic field to produce. We can talk about the electromagnets also. We can talk about the electric field that is linearly varying with time also. But here the major cause we have discussed, that is current distributions. It is followed by Biot-Savart's law, where we are able to get the formula for finding differential magnetic field intensity produced because of a differential current element from filamentary conductor. It was also followed by magnetic field intensity due to infinite filament carrying current and magnetic field intensity due to finite filament carrying current. We have solved sufficient amount of problems based on all these topics. Now here comes the Ampere circuital law, which describes the exact behavior of the current flowing and the magnetic field produced. So let us see Ampere circuital law. Up till now, as far as the bar magnet is given, we had this kind of diagram where the two ends of the bar magnet were shown by North Pole and South Pole, and the lines that are running in the surrounding, that are originating on the North Pole and ending onto the South Pole, these are actually the magnetic flux lines which show the existence of magnetic field into the surrounding. We generally denote the magnetic flux by psi suffix m. If the electric flux lines are there, we have the symbol psi suffix e for electric, suffix m for magnetic. Now, though this is the bar magnet, very common example we learn from the school days in science or in physics, we have the cause of magnetic field to be a charge that is in dynamic condition. So if this is a conductor carrying current through it in upward or downward direction you take, in the surrounding definitely there are such magnetic flux lines generated that represents the magnetic field surrounding to the conductor carrying current through it. So these magnetic flux lines are circulating here. Now if any vector quantity is having circulation, if it is having any kind of expansion, if it is having maximum rate of change of some scalar quantity with respect to the space, we have taken the help of del operator that we are going to further take into the point form of the Ampere circuital law. The most important thing is there that inside the conductor we have current flowing and it is surrounded by the rotating magnetic flux lines. So according to the Ampere circuital law, the statement can be given that according to Ampere circuital law, the integration of magnetic field intensity along a closed path is equal to the current enclosed by that closed path. The closed path is more specifically seen in the example, that is current carrying conductor in one direction. So this is a loop. This forms closed path, you can say. So here, according to the Ampere circuital law, the integration of magnetic field intensity. So magnetic field intensity we represent by H bar. So its integration along a closed path. So closed path it is. So path has a particular length to travel onto. Hence we take the integration with respect to the line. Here the line is a closed line, closed path. Hence H bar dot of dl bar I have to mention. So according to the Ampere circuital law statement, integration of magnetic field intensity along a closed path is equal to the current enclosed by that closed path. So I write here is equal to I suffix enclosed. As current is there, we put the simple unit, that is amperes. So this is the statement according to the Ampere circuital law, and the justification can be given that if the magnitude of the current that is flowing through this particular conductor is varied, the magnetic flux also varies. If I increases, magnitude of current increases, then we are getting more number of flux lines surrounding to this conductor. If I reduces, the number of flux lines surrounding to this particular conductor are also getting reduced. Hence, how much the current is flowing there inside this particular closed path, that is in the body of the conductive material, so that much equal amount of magnetic flux is produced, and we represent that by the closed line integral of h bar dot of dl bar. So this is a simple form given by Ampere's circuital law. The expression according to the Ampere circuital law can also be explained with the help of a diagram. In this diagram, we take a closed path here, okay, or you can consider whatever the conductor carrying current I have shown you. If it is a filamentary conductor, so if you take the cross section of that particular conductor, filamentary, the cross section will be a point, and the current that is flowing through it, that we can show capital I. So it may be outwards from the plane of the paper or inwards to the plane of the paper. So I consider here it is outwards. Hence, the direction of the path, which is having magnetic flux actually, but it is the same direction for magnetic field intensity, what we represent by capital H bar, will be decided. So if this is outwards, thumb in the direction of the current, the curled fingers gives the direction of the magnetic field intensity. So this is the direction here. If we take inwards, we have to take the reverse direction. So according to the Ampere circuital law, we can write here closed line integral h bar dot of dl bar will be equal to capital I in amperes. If we are taking reverse direction, though writing I outwards, the expression will be closed line integral h bar dot of dl bar will be equal to minus I in amperes. So minus sign denotes the reversal to the right hand thumb rule or the right hand screw rule. So this is closed path here. The axis we can write capital X, capital Y axis, and as the magnetic field intensity is following this particular path, at any point it is tangential directed. So this is the direction of the angle phi if you take cylindrical coordinate system into consideration. Hence, in general, we can write h bar is equal to h phi a phi cap, because outwards along the direction of I there is no magnetic flux. Hence, h z will be equal to 0 if we take z axis to be the axis passing through the center of that particular closed path, and it is not getting radially outward. Hence, h rho is also equal to 0. So out of the three coefficients representation in cylindrical coordinate system, we have only one part, that is h phi a phi cap. Now, what can be the closed path that will enclose the current through it? So in general, if this is the conductor carrying current, the closed path may have any shape. It may be circular one, it may be having rectangular shape. Only the thing is, it should have a proper direction according to the right hand thumb rule. So if thumb in the direction of the current, so current should be directed like this. So if thumb in the direction of the current, the curled fingers show you the direction of the closed path on which we have to trace magnetic flux or magnetic field intensity. Now, if any of the loop that does not enclose the complete conductor body, if the conductor body cross section I have shown you like this, and one loop that is going like this, that these 2 points are inside the body of the closed conductor, so that time closed line integral h bar dot of dl bar will be less than I. So if I is the total current flowing through it, or rather we can say I enclosed is definitely less than the total amount of current flowing through it. So this is Ampere's circuital law. Further, I enclose in terms of practical conductor, if you have to express. In the first topic of this chapter, we have gone through current distributions. Thereupon, we have encountered three types of current distributions, that is filamentary current, surface current, and the volume current. So for the volume current, the conductor shown like this. If you take the cross section, through this cross section, how much amount of current is passing. So thereupon we have used the term that is current density, and it is vector type represented by J bar. If sheet of current, that is surface current, is there, thereupon we had used the term to represent current in terms of current density, that is K bar. So this is with respect to the cross sectional length. So it was in terms of ampere per meter, whereas J bar current density was in terms of ampere per meter square. So practically talking, filamentary current we cannot have. We cannot have any conductor to have only surface area, not the volume. Hence, practically we have to write I enclosed given by surface integral J bar dot of ds bar, because any conductor you take, whatever the minute dimensions of that conductor will be there, it will have certain volume. Hence, the cross section of that volume, if you take, it will be the surface area. So onto that surface area, if you integrate J bar, the cross sectional current density, it will give you the total amount of current enclosed. Hence, whatever the relation we have written earlier, closed line integral h bar dot of dl bar is equal to I enclosed. We can represent it using J bar also. So it will have the form onto the left hand side, closed line integral h bar dot of dl bar will be equal to surface integral J bar dot of ds bar, and the unit of measurements will be amperes. So this becomes line integral onto the left hand side, surface integral onto the right hand side. Surface integral means double integral. It will involve two dimensions to have integration. So this becomes the integral form. So this becomes integral form of Ampere's circuital law. So Ampere's circuital law involves circulation of magnetic flux lines representing the directions of magnetic field intensity. So what I talked about the del operator, with the help of del operator we can have the rotation of a vector. Here the current carrying conductor, the current is there, let us say this time downwards direction. So into the surrounding, the magnetic flux lines will be having the direction, the thumb in the direction of the current, and the lines that are showing this direction. So I here, and this is the direction of h bar. Okay. So here we have rotation. So rotation of any vector, if we have, so thereupon we can represent del bar cross of h bar, and that we obtain equal to J bar, that we are going to discuss in more details into the next topic, the curl and Stokes theorem. But this is the point form, also called as differential form, derivative form of the Ampere's circuital law. Now next we talk about the applications of the Ampere's circuital law. So the very first configuration that we encounter for discussion of application of Ampere's law, though it is theoretical, we can talk about it, that is filamentary current. So a filament, that is current carrying a filament carrying current I through it. So for that purpose, if we are going to derive, we can have a simple expression, the surrounding closed path in which the magnetic flux and magnetic field intensity we can represent h bar is equal to h phi a phi cap. We obtain the expression h bar will be equal to I enclosed upon 2 pi rho A phi cap given in amperes per meter. So this becomes the same expression what we have derived for magnetic field intensity due to infinite filament carrying current through it. The difference into this representation of the formula is just that I have mentioned I suffix enclosed in place of I. So H bar will be given by I enclosed upon 2 pi rho A phi cap if we apply the Ampere circuital law to the filamentary current. Further, if we apply the Ampere circuital law to the coaxial cable, coaxial cable is a transmission line we have discussed before. It has two conductors. One is running centrally and another is running surrounding to it, and both are having the same axis which they are going to follow. So considering the symmetry of the diagram, you can just imagine here, this is the coaxial cable. So here, this is the central conductor. From this center, let us say whatever the radius is there, that we represent by symbol small a. From the same center, if we represent the radius of inner dimension for the outer conductor, let us represent it by small b. And if we represent the radius of the outer conductor, that is also outer, so we have to represent small c. So a being radius here, that is the radius of inner conductor, that is solid, it is not hollow inside. The second conductor is hollow inside, and the separation between the first conductor and the second conductor is filled up with certain dielectrics. So this is small a, this is small b, and this is small c. Generally, we have the current represented like this. If this is the current flowing through the inner conductor, the current flowing through the outer conductor is always having the reverse direction. So if this is capital I have to mention it minus I. So certainly we have to apply certain load here to this particular transmission line. So the load will be shown like this. Let us represent the radius, the resistance of that particular device by the load resistance RL. So if we have the current configuration like this and we have to apply the Ampere circuital law, we have to judge how the magnetic flux is surrounding this coaxial cable. So that time we have different regions under consideration. If we apply cylindrical coordinate system to discuss this, let us say this is the rho, because of which we consider a cylindrical shape surrounding to the central axis, rho being the radius of the cylindrical surface. So for the first condition, that is position of the field point that is having inside the body of inner conductor, rho is less than a. So because of the coaxial cable having current flow in this fashion inside the body of the central conductor, that is the location given by rho less than a, the magnetic field intensity according to the Ampere circuital law can be derived with a simple expression, and that I directly give H bar is equal to I into rho upon 2 pi a square A phi cap given in amperes per meter. Here I represents the total magnitude of current flowing through the central conductor and the outer conductor. This is the simple magnitude, 2 pi constant. Small a is the radius of inner conductor, and rho, that is the exact location of the point inside that conductor. Rho is always less than a, and A phi cap gives the revolving direction of magnetic field intensity inside that particular conductor body. Now, if the field point is situated as such that rho is greater than A but less than B, here we have the diagram. B is the inner radius of the outer conductor. So here in between where we are supposed to have dielectric field in the coaxial cable, the field point is located. So at such a position, if we are going to have the magnetic field intensity represented by h bar, we get the expression I upon 2 pi rho a phi cap in amperes per meter. So it is the same expression what we have derived for the magnetic field intensity due to infinite filament carrying current. Because if you take a closed path surrounding to the central conductor, it will affect the same, how much current is enclosed, and that is we have considered while deriving through the filamentary conductor. So it is I upon 2 pi rho a phi cap. There is no role of small a or small b to consider here, because rho is in between the dielectric material, A less than rho less than B. Now if the field point position is as such that B is less than rho less than C, it means the point P is in the body of outer conductor. So here again I show you A, B and C. So here we have the condition rho is between B and C. So in between B and C, it must be into the body of the outer conductor that is having the current flow in the reverse direction with respect to the central conductor. So if the position of the field point is as such, we obtain magnetic field intensity by the expression h bar given by I upon 2 pi rho multiplication with in bracket c square minus rho square in numerator. In the denominator we have c square minus b square, and it is in multiplication with a phi cap to represent the rotational direction of magnetic flux. So this becomes the expression if the field point is in the body of outer conductor. This is the inner radius and outer radius of the outer conductor. Now if the field point P is outside the outer conductor, so more than dimensions A, B and C, beyond C, if this is the position of the field point, let us say rho is greater than C, so that time we obtain h bar is equal to 0. Because the net effect can be seen here, because I that is flowing in one direction through the central conductor, the same amount of current is flowing through the outer conductor. Hence whatever the magnitude of magnetic field intensity could be produced in the surrounding because of only first conductor, that is getting cancelled out by the reverse direction current through the outer conductor. Hence in coaxial cable case, outside the coaxial cable there is no effect of magnetic field intensity, magnetic flux, and that is the ideal condition. So h bar is equal to 0 if we have rho greater than C. Now next we can apply the Ampere circuital law to the uniform infinite surface current. Uniform infinite surface current. So as surface current is there, we can imagine such a plane that is having the flow of current through it, current in this direction from this edge to this particular edge. And for the surface current we have already discussed the term current density given by k bar. So if you take the cross section here, this will be the representation of k bar, and we can represent it magnitude of k into the direction. So the direction will be that of the normal to this plane, that is in which the surface current is lying. So that we calculate by taking the cross product of the direction of the current and direction of the differential length, the position of the field point and the source point we take into the consideration. So using k bar, that is the current density for the surface current, now having the uniformity in the distribution of current and infinite dimensions, so h bar can simply be given by 1 upon 2 k bar cross product with a n cap. The unit of measurement will be amperes per meter. Now the last two cases we have to discuss the application of Ampere circuital law to the solenoid and the toroid. Now solenoid is a practically coil of insulated or enameled wire wound onto a rod-shaped form of solid iron or solid steel or powdered iron. The devices of this kind, that is solenoid, can be used as electromagnets or the inductors in electronic circuits. So here the ideal solenoid can be shown with this diagram. So a cylindrical type of solid body of conductive material, you have to consider here the central axis will be the z axis, the representation of radius by the symbol rho a you take. Now if the cross sectional length you have to take into consideration, this will be the cross sectional length, and we have to represent the current density, that is k bar. So k bar will be equal to Ka a phi cap in ampere per meter. So in the case of ideal solenoid, we have An cap represented by minus arrow cap. It is having the reverse direction. K bar just now we have represented by Ka a phi cap in amperes per meter. Now H bar inside the solenoid will be given by Ka in bracket Ai cap cross product with An cap. This is inside solenoid, and outside the solenoid H bar is equal to 0. So this is the case of the ideal solenoid. If you think about the practical solenoid, I have to show you the turns of wires onto the body of this. So for practical solenoid, we have to show the turns onto the solid body like this. The direction we can show with this type of arrows. So the An cap will be having the reverse direction with respect to the arrow cap. The central axis, the representation of radius y rho will be the same here, but the parameter to be into consideration will be capital N, that is number of turns onto the practical solenoid. So considering number of turns onto the practical solenoid, the H bar inside the body of this practical solenoid will be given by Ni upon D Ai cap cross of An cap given in amperes per meter, where D is the dimension onto the solenoid this way. N we have already discussed, that is number of turns. So this was for practical solenoid. If you take into consideration the toroidal shape, the ideal toroid I can draw with this diagram. So onto this toroid we have to show the directions this way. Now here the cross sections can be shown with the two circles. One circle here, another circle here, considering the symmetry of the diagram. So this has a radius small a. So the field point into the ideal toroid, if we consider the magnetic field intensity H bar, can be given by Ka in bracket rho 0 minus a upon rho in multiplication with, for the direction we have cross product of Ai cap and An cap given in amperes per meter. Here on to this horizontal line passing through this is the position of rho 0 and this is the position of P, and this much is the dimension rho, that is the distance of this point from the center of this toroid. Outside the toroid, as in the case of solenoid, we have magnetic field intensity is equal to 0. Now for practical toroid, onto this toroidal diagram what we have drawn, we have to show the turns. So if n number of turns are there, I have to show the turns like this. So if we continue here, this diagram, this toroidal body will be full of the turns. Let us say n number of turns are involved, capital N number of turns. So that time inside the body of this particular practical toroid, h bar will be given by Ni upon 2 pi rho in bracket Ai cap cross of An cap in ampere per meter. Whereas outside the practical toroid, the magnetic field intensity will be equal to 0. The next topic, we are going to solve certain problems based on the Ampere circuital law and its application to different current configurations. For getting more information to our subject electromagnetic field theory, you can subscribe to Ekeeda channel. Thank you.